Hello everyone, my name is Sven and I work within the research group of Professor Kupnik at TU Darmstadt. In this work, we present a newly developed sensor for bilateral human bite force measurements, which you can already see in the pictures.
In mammals, the lower jaw is movable and the upper is not. Bite force is the force that the movable lower jaw can apply against the upper jaw, as shown here. It is used as an indicator of the functional state of the masticatory system and usually is around 1000 Newton. Bite force is used in research, like, for example, monitoring the therapy success after a treatment against temporomandibular disorders. For measurement, there are multiple commercial systems available, such as the IDTK from Kratos Equipamentos or the GM10 from Nagano Keiki, which are based on load cells and can measure unilateral bite forces up to 1000 Newton. Furthermore, sensors based on piezo-resistive foils exist, which can measure bilateral while having a much higher measurement uncertainty. Since bilateral bite force measurements enable to differentiate between left and right side, force asymmetries can be identified. This allows for further insights in the functional state of the masticatory system, like determining local overloads. In this work, we present a bite force sensor for bilateral measurements with a low measurement uncertainty, which enables determining a force symmetry distribution. So let's discuss our developed sensor. First of all, the force application between the teeth and our sensor is done through the two premolars and the first molar, as according to literature, these are the best teeth for that. For optimal contact, the sensor further is shaped according to the dental arc, describing the average profile of the teeth. The sensor consists of a sensor plate made out of steel, in which 4 commercial load cells with a maximum measurement range of 300 Newton each are held. In order to further hold them in place, they are 3D printed fixtures embedded, and on top there is another sensor plate. As humans should not bite directly on hard surfaces, plastic spacers in combination with the bite registration material is used when inside a human mouth. As the thickness of the spacers can be varied, the bite force over multiple mouth openings are measurable. In order to determine the measurement uncertainty of our sensor, we put it in our universal testing machine Inspect Table 5, in which our sensor was loaded according to the EUML R60 guidelines. The sensor was loaded unilaterally, bilaterally and bilaterally, but being inside a jar model. With this test, we wanted to see how the sensor behaves under non-optimal force application conditions due to teeth or asymmetrical force application. The uncertainties given here refer to twice the standard deviation and certify a linearity error of 1.2% of the sensor. Furthermore, as we can measure the force individually for every single load cell, we can measure asymmetries in the bite force. In order to quantify how good we can detect these, we look at how much force the individual sites measure during a unilateral load. With this technique, we observe that starting from a load of 100 Newton on, the residual force flow through sensors that are not actually loaded is less than 4.1%. We can conclude that we have achieved our goal of developing a bite force sensor that can measure the bilateral bite force with a low measurement uncertainty. In future work, we want to verify our sensor with real human probants. We also want to measure the bite force from patients suffering from TMD, from which we hope to get insights to objectively support diagnosis, as well as therapy research. And with that said, I want to thank for your attention and would like to open the stage for questions.